In this video, we're going to introduce trigonometry in the context of the unit circle. All a unit circle is a circle of radius 1. So the term unit in math, when it's used to describe objects like a unit square, a unit circle, a unit triangle, that usually indicates that you have side lengths or some aspect of the figure being described that has length 1. So in the case of a unit circle, this inner circle right here is a unit circle because he has radius equal to 1. What we want to do is look at our definitions for the cosine and sine functions. So we'll suppose that we have some angle theta right here. And let's suppose that we have some point right here, xy. And then let's think about how the cosine of theta has been defined for us. So the cosine of theta has been defined as the x-coordinate, right? We construct a right triangle and then the x-coordinate is the numerator, and then we're supposed to divide by the radius, where the radius is the length of the line segment from the origin to the point xy. So this is the radius, and as we saw earlier, the radius is going to equal the square root of x squared plus y squared. That was just by the Pythagorean Theorem. And notice that if you multiply both sides by r, that we get a description of x that is in terms of the radius of the circle on which the xy coordinate lies, and theta, the angle in standard form that we make with the positive x-axis. So we can actually rewrite the ordered pair xy using for x r cosine of theta, and then we can do something similar for y. We can say, hey, the y coordinate has been used in the definition of the sine function. We know that the sine of an angle theta has been defined to be the height of the side opposite the reference angle, the signed height, or the y coordinate divided by the radius. And if we multiply both sides by the radius, we get that y is just equal to the radius times the sine of the angle theta, r sine theta. So we can always replace x and y with r cosine theta, r times sine theta, if we know the angle theta and we know the radius r that the point xy makes with the length r that the point xy is away from the origin. So notice on the unit circle then, this would actually simplify, because on the unit circle the radius is 1. So we would actually find that r cosine theta would give us 1 for the radius times cosine theta, comma, times 1 for radius times sine theta, which just simplifies to cosine theta sine theta. So on the unit circle, to locate a point xy, we just need to know the cosine of theta and the sine of theta to locate a point. The radius is 1, so things really simplify for us. Note that the cosine of theta, as we mentioned earlier, is defined to be x over r. So if all I have is the cosine of theta here, if I have any point xy given by r cosine theta, r sine theta, I can find a point on the unit circle just by dividing x by r. So this is going to be cosine of theta is x coordinate over radius, and get that out of my way. From here, we saw that the sine of theta was just equal to y over r, so sine of theta can be replaced with y over r. So given any point on any circle of radius r, we can actually dilate it to be a point on the unit circle by multiplying the point xy by a factor of 1 over r. It will shrink or stretch that point onto the unit circle as necessary. So these are a couple of key results. One, any point on any circle, any point xy can be represented by r cosine theta, r sine theta. And on the unit circle, we have a special case where the x and y coordinates are just given by the cosine and sine of theta, or x over r, comma, y over r. So here's an example of how we can apply this. It says, consider the points that lie on circles of radius 1 and 4. So down here in the picture, I made a circle of radius 1 and a circle of radius 4, and that lie on the terminal side of an angle in standard form of 4 radians. Find trigonometric representations of these 2 points. So the first thing it might be nice to do is figure out where 4 radians is in the context of the xy plane. And we remember that a half revolution, or 180 degrees, is pi radians. But pi is about 3. So this is about 3 radians to here. And if we rotate an angle theta through in standard form all the way to the negative y-axis, that is 3 pi over 2 radians, and which is about, if pi is about 3, this is about 3 times 3 over 9, or 3 times 3 over 2, sorry, which is 9 over 2, which is about 4.5 radians. So a 4 radian angle is going to be between here and here, but closer to 4.5 than it is to 3. So if we're trying to draw a rough sketch, we might draw something that looks like this. Here's a line coming down. We have an angle theta in standard form. That is equal to 4 radians. There's a reasonable depiction of that angle. And we're asked to find the points that lie on the circles of radius 1 and 4 that make this angle of 4 radians in standard form. So we're being asked to find trigonometric representations of each of these 2 points. This point here is simple. We're on the unit circle. This is a circle of radius 1, which means that the cosine of the angle 4 radians, comma, the sine of the angle 4 radians give us the x and the y coordinates of that point. So a simple representation, we could plug cosine of 4 and sine of 4 into our calculator to get rectangular xy. Estimations for those, if we needed to, as long as we made sure we were in radian form. And then we recognize that this point here, which is a radius of 4, can be easily represented using trigonometry as well, because as we saw a moment ago, any xy coordinate in the plane can be represented by r cosine theta, r sine theta, and we know r is 4, and we know the cosine of the angle, so we can write this as 4 times the cosine of 4 radians, comma, 4 times the sine of 4 radians, and there we have trigonometric representations for both of these points with a reasonably accurate sketch to go with it. Finding a point on the unit circle, so let's suppose that the point x, comma, root 6 over 3 is a point on the unit circle lying in quadrant 2. Find the values of all 6 trigonometric functions of theta, where theta is the smallest positive angle, so we're going to want an angle that is between 0 and 360, or in radians between 0 and 2 pi radians, whose terminal side is the ray that contains this point. So probably first step is just kind of quickly draw a picture of the situation that you find yourself in. We are on a unit circle. Pretend that's a unit circle. And we are in quadrant 2, and we have this point xy that's lying on a ray. Here's our angle theta, and we need to find the trigonometric function values for theta, and we have this point x, comma, and root 6 over 3 that's lying on the unit circle right at that point. So the key here is that because we're on the unit circle, we know r is equal to 1. So I can just use the Pythagorean theorem to calculate x. In other words, In other words, if I give myself a little bit cleaner picture, and I just draw this in right here, this is x, this point is x, root 6 over 3. And if I drop a perpendicular down, I have a right triangle. I don't know the width of it. The signed width is x, but I know the height, the y coordinate is root 6 over 3, and I know the radius is 1. So using the Pythagorean theorem, I get the square of the hypotenuse is equal to the sum of the squares of the legs of the triangle, and one leg is x, that's the unknown distance, and then the other leg is root 6 over 3, and then we just do some simplifying. Square root of 6 squared is 6, 3 squared is 9. This would simplify to 2/3. Subtract 2/3 from both sides will leave us with a 1/3 here. Take the square root of both sides. Usually we get plus or minus, but in quadrant 2 the x coordinate is going to be negative, so we want the negative square root. So we get negative. Square root of 1 is 1. Square root of 3 is already in simplified radical form. This is x, and if you want to, you can rationalize this. Again, I don't think that you need to, but you can. So we get negative root 3 over 3 as our x coordinate right here. Here's negative square root of 3 over 3. And then our job is to find the values for the 6 trigonometric functions. Well, we're on the unit circle, so we know that the cosine of theta on the unit circle is just the x coordinate. The x is the cosine of theta on the unit circle, and y is the sine of theta on the unit circle. So cosine of theta is just the x coordinate, so negative root 3 over 3. Its reciprocal is the secant function, so it's going to be the reciprocal of this, which is negative 3 over the square root of 3, which we could rationalize if we needed to. The sine of theta is going to be just the y coordinate, which is the square root of 6 over 3. Its reciprocal function is the cosecant function, so the cosecant of theta is going to be the reciprocal of this, or just 3 over the square root of 6. And the tangent function is going to be y over x, so we're going to get the square root of 6 over 3 divided by negative square root of 3 over 3. And then this will simplify, those will cancel, we'll get negative square root of 6 over square root of 3. And we could clean this up a little bit if we wanted to. I mean, so something that we could do if we wanted to. Tangent of theta equals negative. We could recognize that the square root of 6 is really the square root of 3 times the square root of 2. This would be something we could do. And that would simplify to negative square root of 2. So we could simplify that. And then that would make the cotangent function the reciprocal of this, which would just be negative 1 over the square root of 2.